names kill me. Why is not pronounced?
Yes, yes, perfect.
Yes.
Yes.
Okay. Okay, we are at time to start. So this morning's session is, sorry? But we can't wait longer. Otherwise, it's 8:45.
So, but then can we run into the break then? Can we run into the break?
Yeah.
So we can go into whatever.
Just extend by half an hour into the break.
So we start at 9 then? Did you say we should start at 9?
I mean, you're the boss. If you tell us, we'll do this. Okay, all right. We'll just shift back. Okay. All right.
Should I go?
No, let's first make the final decision and then.
Some people out here because they read it, and some people are.
Yeah. By the way, I can tell you something fun about SLT. So the second SLT was held in Goa. In Goa. Okay. And Srinivas Bangalore was the general chair. And we were staying in Goa. Is not a very big city. It's very tiny. So the hotel where the conference was didn't have enough capacity. So people were staying in 3 or 4 other hotels, which are like maybe 1-2 kilometers away. And Goa doesn't have good public transport either. So there was a conference bus that used to go around and pick everybody up. And so every day in the morning, the session would start when the bus arrived, not when it was published. So the first day I was panicking at the hotel. I'm like, the bus is not here, the session is about to start. What's happening? I'm going to get a taxi. And the hotel guy says to me, relax, your bus will come, your bus will come. And they used to call it the IEEE conference. IEEE. It was IEEE, IEEE conference. So I was like 25 minutes late. Okay, and I was like, shit, I missed the opening presentation thing. And I walk in with a few others and Srinivas says, okay, the last bus is here. We'll start in 5 minutes. And then lunch was supposed to be somewhere, but the weather was really nice. So went to the hotel guy and said, we want our lunch on the beach. And so announcement, okay, today's lunch menu has been moved from the atrium to the beach. It was like, having a party at home. Okay, everybody over here.
I understand. This is good. It's a
good size meeting. So, yeah, I was a bit worried, but if Bhuvana thinks we can extend, because I don't like putting in the other sessions.
And I don't have the feeling that people are not having conversations and staring at the screen. Right?
Yeah. Yeah, that is true.
In that sense, you know what? The setup with the tables is perfect.
Yes.
Otherwise, you have this long
classroom style seating.
Yeah, then
it's not conducive.
It would be different. Right.
So we did this, the Amazon initiative we have outlined. The initiative we have with Amazon, the Amazon site. So we did a meeting of that in October. There were about 110 people there.
110?
Yeah. Wow. So we had the same format. We had round tables. It was great because Amazon people scattered themselves throughout the room. There was one on roughly every other table. And people just talking to each other.
Yeah.
Doesn't work beyond like about 150, maybe 200.
Well, we had 200 here, right?
Yes, this is about the limit. Anything bigger, let's say double this and it doesn't.
Oh, thank you.
I probably would have been the only
So the way I'm looking at it, the closing ceremony is 12 to 12:30. So if we delay everything by half an hour and then use the coffee break by 15 minutes, then we end up 15 minutes late, and I don't think anything happens.
I had the impression that anything a little bit late here.
No, more importantly, the hotel's not going to say, oh, we have another event, clear out.
Oh,
We have the room for the rest of the day. So on the
so
starting
should I
point,
tell people to keep the posters up until 8?
yeah. So the starting, for example, there was an issue, and maybe you were on that call when we talked about it. So we wanted to test the audio video the previous day to make sure the AV works, and they said we cannot do it until after 9 p.m. So Bhuvana and Ahmed came here at almost midnight, and when Shinji and I went to drink beer, they came here to test the AV. The reason is that they had another event. And they said the room belongs to the other event until 9 o'clock.
Yeah.
But anytime after that, you can. So in the same way, this room belongs to us for the rest of the day. So if we run over by a bit,
Okay, good morning. Welcome to the session on the reporting of JSALT's results and Superb Challenge. The session starts delayed so that more people can have the pleasure to see it. It will be presentations of 15 minutes, including question and answering. The first presentation will be given by Sanjeev. Then we will have a video played from Anthony, who led the multilingual speech-to-speech translation for under-resourced languages team, followed by Shamur's presentation on multilingual and code switching for ASR. And then we will have a presentation by Hangi on leveraging pre-trained models for speech processing, which will then also transition into the Superb Challenge. Okay, Sanjeev?
Okay. Good morning. I'm Sanjeev Kudanpur. I'll tell you a little bit about how these JSALT workshops come about, or perhaps how this summer's workshop came about. And then we'll follow it up, as Thomas announced, with the presentations by the three team leaders. So JSALT, a little bit of history. It started off with an idea that actually comes from something called the Institutes for Defense Analysis, the one in Princeton. Over many years, starting in the 1950s, they have a tremendously successful history of tackling really hard problems in cryptography by bringing together mathematicians to Princeton for 10 weeks in the summer, and they work closely together. And this was a big success over the years. And people, mostly from the US government research community, wanted to employ this idea for speech and language technologies. So people like Jordan Cohen and others said, okay, we'll help do this for speech. And those of you who are older will remember Jordan Cohen. Those of you who are younger just know that he was one of the more senior people in the field. And so they started this, and the first couple of workshops were actually held at Rutgers, because Rutgers is close to Princeton, and it was easier and Jim Flanagan was there. And in '93, the Center for Language and Speech Processing was formed at Johns Hopkins, and Fred Jelinek, who's another luminary in the field, came to be its director. And with him, the workshops came to Johns Hopkins. So 1995 was the first JHU workshop on speech and language. Just to give you a little bit of perspective, the error rates on switchboard, the best systems were at 55%. That means we got more words wrong than right. And on Spanish call home, the error rates were about 80%. So this is when the workshop started, and everybody said, okay, these are hard problems, we need to work on them. Of course, you all know where we are today, but you should sort of remember how this came about. The workshop had many notable outcomes and let's just call them alumni over the years. But before I do that, let me tell you how these workshops are run. By the way, SLT is a workshop, ASRU is a workshop. So JSALT is not a workshop in any of those senses. The focus is on work. So we work intensively together for 8 weeks on a focused problem on some topic in speech and language. And typically we work on 3 to 4 topics. And each topic is handled by a mixed team. So there are senior researchers, professors, and other leaders from industry. There are PhD students, And one of the things we added at Hopkins is we started throwing in undergrads because they're more fun, energetic, and like somebody at Hopkins once said, they can solve problems because they don't know they can't be solved. So somebody says, oh, this is impossible, and some undergrad comes along and does something fun. So we started including them. And that's a typical team, about 10, 12 people. And the goal here is to create synergies. Like, the one way to think about it is the Manhattan Project, when the US undertook this, they put together the best brains in the country, or even better, the NBA, the dream team to the Olympics that the US sent. Once they were allowing professionals, they took the best players from the NBA, and that team did great things. So that's the kind of thinking you want to do here. But the main thing that comes out of the workshops is actually many, many very long-term collaborations. And this history is really long and illustrious about how once people work together for 2 months, you start understanding each other. You do many more good things together. But there are also lots of very good outcomes. So the Giza tools came out of the 99 workshop. Those of you who remember SuperSed made great advances in speaker ID, the Moses machine translation tools, iVectors for speaker ID, Kaldi, ESPNet, and I can go on. So there are a bunch of things that have come out of the workshops that have sort of changed the landscape. Our other legacy are people. So at this point, about 500 plus star students have gone through. It's a very intensive, amazing experience for the students, and they all remember it. So Yasser, who gave the keynote yesterday, is a summer workshop student alumni, so are many others. So it's basically, these people have now gone out and are in very influential positions in industry and academia and everywhere else. For example, second from the right up here is Eric Brill. He was in the 99 workshop, I think, or 98. And he went on to become the VP of research for eBay and PayPal and everything. In the photograph on the left, far away in the corner, is Jeff Zweig, who's now with Meta, and Jeff Bilmes. They brought graphical models to speech recognition. Peng Shu, who went on to work at Google Translate. Talking of Google Translate, the photo on the right is Franz Ock. He actually started Google Translate. And next to him is Alex Fraser, who was then a student, now a professor in Germany. The workshop also tackles problems way ahead of when they become popular in the community. So Manmatha on the left was working on joint image and text models in 2004. And we made some progress. Of course, today, as Jim Glass said in his remarks, like we've got representations that make it much easier, but we were working on it even back then. And Manmatha later on went on to join Amazon's visual search team. Search, as you know, is very important in many industries. So this was searching for product images with text or text with images and so on. On the right is Philip Kuhn. He literally wrote the book on statistical machine translation, and last year he wrote the book on neural machine translation. Najim Dehak, who came up with iVectors in some workshop. Dan Povey, who started Kaldi work at the workshop. I could go on. In a few years, I'll add Shinji and others who did ESPNet and things like that. Anyway, one of the things that happened is, for the most part, from 1995 to about 2013, the workshop was always at Johns Hopkins. And at some point, I got tired of organizing at Hopkins. I said, why am I stuck at my place in summer when other people get to go to other fun places? So in 2014, we had the workshop in Prague. 2015, we went to Seattle. You can't see it over here, but right here somewhere, there is actually, what's the mountain in Seattle? Mount Rainier, yes, you can see it over there. This is actually a picture taken from outside the JSALT building. So we started, 2019, we went to Montreal. To 2017 in CMU, 2019 in Montreal. Next year, we're going to be in Le Mans. So we do 1 year at Hopkins, 1 year away. Of course, people think of it as a summer workshop, but for all the organizers, it is a year-round activity. So the way these workshops get put together is that you start with a call for proposals, and people get ideas. And let me just walk you through it. So for example, for this year, this summer's workshop, back in September of 21, we put out a call for proposals. We said, hey, we're going to have the workshop. Do you have any ideas? Send us just a one-page idea or less. And let's see what you have in mind, and then we'll figure out based on that how to proceed. And we sort of give broad topic outlines. We want, in speech processing, we want to focus on under-resourced languages. In NLP, we want to look at knowledge representations. We're interested in HLT for healthcare. We're interested in computer vision and HLT sort of at the interface areas, and so on. In response, we got about 12 proposals. One of them was sort of totally not possible to do in a workshop format. For the other 11, we put them through an interactive peer review. So all of you are used to peer review. You submit papers to conferences or proposals to funding agencies. It goes into a black box, a black hole, and outcomes an outcome, sometimes favorable, sometimes not. Our review process is very different. It's interactive. So we had 34 researchers and 15 were virtual. And what I meant by interactive is the authors of the proposal are also in the room. So you actually get to propose, and the reviewers react, and you discuss with them. And so 7 authors were there in person. Authors of 7 proposals were there in person. There's sometimes more than 1 author per proposal, and 3 virtual and 1 by proxy because they had some time zone difficulties. And basically what happens at this meeting is you present the idea, people critique it, and then the boldface, we collaboratively try to improve it. We say, how can we do something to fix this? And you do this many, many times, starting Friday, 6 p.m., going until Sunday. And at the end of it, then we do a proper review. We say, okay, let's evaluate them and rank them. And we have a pretty elaborate system of figuring out the sentiment of the reviewers. It's a ranked choice system. So if the proposal you like the most doesn't make the cut, your vote gets transferred to what you think is the next best proposal, so that there is no need to game your voting and say how to do it. Just vote your true preference and things work out nicely. There's a way to manage conflict of interest and so on and so forth. So this is the proposal review undergo. So this is how the workshop topics are picked. So we did this last fall. The meeting was, like I said over here, December 3, 4, 5, and 3 topics were picked for the summer. The first one was multilingual speech-to-speech translation for under-resourced languages. This team was led by Anthony Larcher from Lamont University, and here are some demographics of the workshop team. There were 13 senior members, 11 students, and here's a little picture. Not all of them were here because some of them were remote and so on and so forth. The second team that was picked was on multilingual code switching speech recognition. This was led by Ahmed Ali, who's here with us, and this team had 9 senior members, 11 students. Again, here's a picture of the team, and you'll hear more about each of them one by one. And then the third team was led by Hang Yi, who's over here, and it's worked on leveraging pre-trained models for speech processing. Again, this team, you don't see the full team picture here because some members were remote and so on and so forth. So I could stop here and say, okay, there were 61 participants this summer, 49 of them full-time in Baltimore, and another 12 part-time. But let me make a couple of quick remarks about what else happens in these summer workshops. So first thing, we actually spend the first 2 weeks in intensive training of the students. Like every day there's about 7 hours of instruction, 3 hours of lectures and a 4-hour lab on various topics, NLP, machine learning, information retrieval, machine translation, speech recognition, speaker recognition, and so on and so forth. The idea is to bring everybody up to speed, make sure all the students understand what the other teams are doing, not just the team they're in, and so on and so forth. The other thing we do is we have plenary lectures. So while we're intensively working on these problems that we've chosen, we also bring in experts to come to talk to us about other topics, just to broaden our minds, change the way we think about our problems. So Nizar Habash was mentioned a couple of times here for all his work on dialectal Arabic. He was there. Several people referenced the low language left behind work from Google, from Meta for translation from many languages. So Ann Lee led that team. You heard from Preslav yesterday, the day before. Feroz talked about that work on fake news detection and so on and so forth. So this is the kind of things we had. Of course, we were still in the time of Corona. One of our plenary speakers had to withdraw because he was struck by Corona the day before his arrival, and so on. The third thing we do, of course, is we have fun. So it's one of those work hard, play hard attitudes. So like Baltimore, of course, you're going to have steamed crabs. So every Thursday we go out as a group to have dinner. We celebrate 4th of July, which happens to happen in the middle of the workshop all the time. This year, there was a big French delegation, so we also celebrated Bastille Day, or as they call it, the French National Day, by having a barbecue on a rooftop. So it's basically a fun time. It's very memorable. And all that is, of course, made possible by funding from various sources. So this year it was funded by Google, Amazon, Microsoft, and one of the teams was funded by a European Commission grant called Esperanto. So this is JSALT. Let me then move right on. Thomas, what should we do next?
Well, I think we have time for one question.
Okay. Thank you.
Do you have a question? I have a quick question.
Yeah.
So which space should people look at to see when the deadlines for the proposals are due?
Oh, yes. So where should we see for the next proposals are due? So I should have said this. We are now in January, so we've already gone through the call for proposals for the 2023 workshop. The call went out in late September. We had our planning meeting in December 16, 17, 18. It was, this time the planning meeting was big. There were 50 people participating, about 40 something in person, and another 8 or 10 remote. And we have chosen, we've basically got a ranked list of topics, and we're in the middle of figuring out sponsors and which ones have most support among the sponsors. So one topic most likely will be on differentiable FSTs, like basically the equivalent of Google's Open FST, but with the AutoGrad built into it. There's another team working on document representations that are beyond just BERT or BERT-like things, which focus on the content, but instead look at where the document lives in relation to other documents. So they're going to use citation graphs and other ways documents relate to each other to get a more meaningful representation of documents for search and understanding. And then there's a team that has proposed to work on children's speech, another team that has proposed working on audiovisual diarization, and so on. So these will come out on the Hopkins website very soon, and the workshop itself is going to be in Le Mans.
Okay, I think this is very useful information. Okay, so the next presentation, unfortunately, Anthony Lachey couldn't come, so we will have a video.
Let me add that actually some members of his team are here. Themos is here, Gail was here, and Mikhail was here. So you guys should answer questions if need be.
Okay. Let's see. Oh, why is that not on the right screen? We should have tested on. Oh. The screen. Oh, that will be fun. Can someone help me navigate the... Where's the mouse? No, the mouse is... No, it's not. I cannot find the play button. What are you doing? It's in the browser, yeah. Okay.
Focus on under-resourced languages.
Okay, let's start from the beginning.
I'm Anthony Larcher, coordinator of the European project Esperanto.
Maybe a little bit louder.
The Esperanto project aims at
Okay,
developing sustainable speech technologies able to interact with humans while providing a special focus on under-resourced languages and evaluation of new. The consortium of Esperanto involves Avignon University, Allo Media, Brno University of Technology, Senatav, CONICET, Elia Data, Johns Hopkins University, Le Mans University, LNE, Mila, Omilia, Phonexia, the University of Chile, Grenoble-Alpes University, UNIMAS, University of Saragossa, the University of Sheffield, and the University of Saints. During the last summer, 23 researchers from this consortium have been joined by 4 additional researchers from Microsoft, Naval Labs, and MIT in order to work on multilingual speech-to-speech translation for under-resourced languages. To achieve this goal, we considered the example of Tamashek. Tamashek is an African language spoken in Algeria, Libya, Mali, Niger, and Burkina Faso, and for which annotated corpora were very limited at the time of the project. When we started this project, we could only rely on 17 hours of spoken Tamashek that were translated into written French. Note that this dataset has been released for the IEEE SLT 2022 evaluation and is publicly available. I'm now going to describe the starting point of this work, the paradigm we have considered, and the questions we've tried to address. The task we intend to address is speech-to-speech translation. It consists of producing a speech signal in a target language given a speech signal in a source language. Additionally, we want to preserve some paralinguistic information conveyed by the original source signal, such as the identity of the speaker or the emotions, and we intend to address this task in the context of under-resourced languages. In the case of TamaCheck, limitations due to the data are twofold. First, having only French-aligned data, translation into another language cannot be learned directly. Second, having only written French as an aligned resource makes it impossible to transduce directly speech from a source language into TamaCheck speech. Actually, resources for speech-to-speech translation of even high-resource languages are still also very limited. One way to leverage more knowledge for speech-to-speech translation is to consider multimodal translation from a source language into a target language. The information gathered from a second modality, like text, might benefit the audio modality if we manage to share the knowledge of languages between the modalities. Another way to leverage knowledge is to consider different source languages, for instance, two source languages that will help develop the decoder to generate the target speech. Here, we have chosen a strong assumption that considers that for all different languages and for both speech and text modalities, a same sentence can be represented as a single point in a cross-modal and cross-lingual embedding space. According to this assumption, we would like to design one or several encoders that will project two sentences with the same meaning, either written or spoken, from two languages into a single representation in the common space that will then enable us to generate text or speech into the target language. The question is now how to define that common space and how to project all our data into it. Our starting point was to consider existing multilingual systems like LAPSI that have been trained to project written sentences only from different languages into a common multilingual space. Based on LAPSI, two of our colleagues proposed a system called SAMU-XLSR that relies on a frozen version of LAPSI and that trains a version of XLSR to create an audio encoder that projects spoken sentences from different languages in the same space as the written sentences processed with LAPSI. During the training, speech embeddings produced by XLSR are pulled towards their written equivalent extracted with LAPSI. At the end of this process, SAMU-XLSR produces audio or text embeddings that are aligned across languages. This system was the starting point of our work last summer during JSALT 2022. The main limitations were that both written and spoken sentences were encoded into a single embedding, which might not be enough to generate the target speech signal in the target language. We did not have any decoder to generate neither speech nor text into a target language, as this first version of SAMU-XLSR has been only validated for cross-lingual and cross-modal information retrieval. Now that I have introduced the task and our starting point, I can list the main goals we've addressed last summer. A first group ran an extensive analysis of the cross-modal and cross-lingual space in order to understand what semantic and acoustic information was conveyed by the embeddings. A second group has been working on the generation of speech and text from this common space, while a third group was developing automatic metrics to evaluate speech-to-speech translation directly from the audio signal without having to transcribe the speech. I'm going to briefly describe the results obtained by the different groups. For more details, you can watch the complete presentation online. Now that due to the time constraint, I only present here a part of what has been done during this workshop. Amongst the many analyses that have been performed on SAMU-XLSR, common space, we've tried to see how the speech embeddings were performing for cross-lingual semantic extraction. Experiments performed on media and port media, two corpora in French and Italian, annotated with semantic information, have shown that SAMU-XLSR extracts the semantic content independently from the language. Compared to XLSR, we observe that SAMU-XLSR captures and encodes the semantic information for both Italian and French languages. Thanks to this additional semantic training, a downstream model used on top of SAMU-XLSR is able to perform well in a language for which downstream model has not been trained. This training, however, leads to some degradations when changing the downstream task to speech recognition, for instance. This was expected, as the loss function used to adapt XLSR into SAMU-XLSR focuses only on semantic and not acoustic anymore. In the same manner, an acoustic analysis of the embedding space produced by SAMU-XLSR confirms that the constraint of a semantic loss produces embeddings that convey less speaker characteristics and that will probably be less interesting to carry the speaking style or the emotions of the speaker across languages. Additional experiments have shown that the acoustic information conveyed by the SAMU-XLSR sentence embeddings is not sufficient to reconstruct good quality speech signal. It is thus necessary to preserve a temporal information through the use of a sequence of embeddings. Another part of our work has thus focused on generating sequences of text and speech samples from the SAMU-XLSR framework. Starting from the sequence of embeddings available before sentence level pulling into the SAMU-XLSR model, we fine-tune the SAMU-XLSR together with an embarked decoder in order to generate text in different languages. We can see on the graphs for different groups of languages that embeddings from SAMU-XLSR outperforms classical XLSR for speech and speech-to-text translation. You can see the blue score of the different categories of languages. It's especially true for the case of low-resource languages. In order to directly generate speech from speech, we replace the embarked decoder with the embarked unit decoder and then process the sequence of tokens generated by the decoder with a hi-fi GAN unit-to-speech vocoder. Evaluation of the translation is then performed after speech transcription of the target language. So note that we have to come back to the text in this evaluation. So it shows that SAMU-XLSR outperforms XLSR to encode speech into a sequence of embedding for speech-to-speech translation. Extending the pipeline to translate text to speech, we've been able to perform translation in Tamacek and reach a new baseline for this task. I will now finish this very brief summary by introducing a work done to enable the direct evaluation of speech-to-speech translation. This work is motivated by the need of evaluating speech-to-speech translation without relying on ASR, because some languages like Tamacek have no fixed written form, and sometimes you don't have the resources to train a proper ASR system in the target language. Amongst the approaches tested during the workshop, we adapted the COMET framework, that comes from machine translation, in order to produce a translation score given to spoken utterances. As you can see on the last line of this table, we obtain good correlation with scores from translation of the written utterances, which let us hope that this framework can still be improved and widely used for the task of speech-to-speech evaluation. A publication is available on arXiv with the details of this work, and more experiments are still going on. Now, as a conclusion, we can highlight the use of a cross-modal and cross-lingual representation space that has led to significant improvements for speech-to-speech and text-to-speech translation. We try to answer the question whether a cross-modal, cross-lingual space could exist, and despite the semantic alignment that is promising, we think that it can be interesting to test with concepts that are deeply cultural in order to evaluate the effectiveness of the cross-lingual space. Note that a purely semantic training of this space does not preserve the acoustic information and thus is not sufficient to train proper speech-to-speech systems. Working with under-resourced languages, we made great progress, and we think that more progress are still possible by leveraging on other languages. A couple of studies have been done during the workshop that we didn't have time to report in this presentation. We improved the performance for the task of any language to English, but English to any is actually more challenging because we most of the time lack of speech data, aligned speech data. So we think it could be possible to get better results using family-specific models, but the work is still going on. Then we think it's possible to align sequences of representation across languages, but some work going on based on the speech-T5 framework haven't shown any progress so far. Then, the last but not least, on the side of evaluation, one question is how language portable is a train metric, and can we trust it in a new language without a text reference to validate it? I thank you for your attention, and I thank you in the name of the Esperanto team, looking forward to more progress on this work. Thank you.
Okay, due to the nature that it was a video, there will be no question answering. I think, Shamu, you are up next, yes. Let's see if we can get this set up. I think we had this setting to go back. Display setting. Stop. Mirror is fine?
Yeah, mirroring is good.
Okay, so. Did I get the right one?
No, I need the same.
Okay. Oh, yeah, sorry. That's. Super, no. Where did it go? This one. This is the one that I received from you, right?
Okay, let me open it. Presentation. From start. Business. Okay, good. Hello, everyone, and good morning. As Sanjay was saying that we spent quite a few weeks, almost 6 to 8 weeks in Baltimore to try to figure out how to model code switching in the ASR. So before going to code switching, I wanted to say something is that last few days during the conference, we have been listening that multimodality, multilinguality. These are the terms. These are not just research. These are now a practical need that every speech technology needs. Because as we are connecting with more people, we are learning more languages, we try to communicate with each other, there is a chance that this behavior of ours are becoming innate in nature. So the moment we use speech technologies, for example, ASR, we don't think that how this technology will act. We want the technology to bring our what should I say, necessity in mind. We shouldn't act off that, but the technology should act, or how to say, they should adapt to our behavior. Anyway, So keeping that in mind, if we want to have a robust ASR, multilingual ASR, we have to deal with code switching. Now, this is a very long list of people that are in the team. All the graduate students, they did a lot of work, and I will try to present their work properly. And I guess, yes, and if you have any question, you can ask me, and also please reach out to them. They did most of the work. So, as I was saying, code switching is not a different phenomena. It's not separate. It's integrated. The moment a person can speak two languages, they themselves may intentionally or unintentionally changes the language, changes the word between them, or sometimes sentence between them. So when we change in long term from one sentence of language one to another, it called can you see my, okay, right? It called intersensual code switching. Whereas when we do short changes between the words, it's called intrasensual. So, one of the biggest issue when we try to model this code switching is data. We have monolingual data, but code switching is a phenomenon that we use sometimes in our daily life, in spontaneous conversation, and we don't have access to that much of data. So what we wanted to do during this summer is to find out how to model code switching with limited or zero resources. So to do so, we prompt for the approach where we use monolingual corpus, and then using those corpus we try to model a bilingual model that should, by nature, learn how to deal with code switching. So, before modeling code switching, we just wanted to know what this phenomena is, not just by doing blindly some experiment, but to understand it. So what we did is we first learned how to characterize this code switching, and then we tried to play around and see how can we generate synthetic code switch data, followed by different modeling techniques to see if our data is actually helping us, and then we try to see the models that we creating is actually good, or there is some issues in our evaluation. So these are the, apart from this, we also did few other things, but for time limit, I will just go over quickly with this thing. First, to understand the code switching behavior, Electra and all other students first tried to understand what motivates people to do code switching. In this case, we saw different factors that we could study. That includes age, gender, education, personality, among others. However, what we noticed is all these factors are language independent and wasn't highly, we didn't get any significant findings that we could generalize through all the languages. However, one thing that we found is highly correlated with code switching in corpus level was formality. Formality in the text. We noticed, for example, in Spanish, when the language is highly formal, there is a chance of having more code switching than in English. Kind of makes sense, right, in monolingual data set. So if you want to say something technical or something very powerful enough, you might switch to English words, whereas for English, you don't need to switch to Spanish. So apart from that, we also did few other matrices and tried to find correlation with gender and others. We didn't find anything on that. Now, we wanted to see, the biggest problem that we have was lack of data. How can we solve it, right? Now, it's really hard, as I was saying, it's really hard to access the code switching data, and even though if we had this data, we cannot generalize it, because the pattern of manifesting, and when the code switch manifests, is totally different, is diverse, and never follows a unique style. So what we did, we tried to play around with the monolingual data and then generate code switching. For text, we tried two approaches, one with parallel text and another is utilizing the pre-trained model. So we did, for time's sake, I'm just going to talk about a little in the parallel text, what we did. We have two data sets, text language 1 and language 2. So how can we create parallel data set that goes in both ways? So taking the first language, we use machine translation to get the second pair. And then using this pair, we used alignment, parsing, and different code switching generation. For the code switching generation, we could use linguistic theory like equivalence constraint, or we could randomly replace the lexical. In our case, what we noticed is that when we generate random lexical representation, we have a gain not in perplexity, but also in word error rate. Maybe some regularization effect is happening there. But when we do some constraining, that code switch, you can have a certain amount of distribution for code switching, this performance actually drops. However, looking into this, the adding code switching text doesn't change any performance drastically. It doesn't improve that drastically. Another one that we checked using the same parallel text is to use translation model. We trained a unified translation model that goes from L1 to L2 and the vice versa. And then we use this shared Latin embedding to generate code switching utterance. Even over there, first when we tried normal decoding, we noticed that the model just generates monolingual data. However, when we added a constraint decoding with some code switching point, the minimum code switching point, we noticed some results that has code switching generation. However, if you see this compared to the real code switching model, which is the top line result, and no code switching, that is the monolingual model, we have some gain compared to the monolingual model, which is still insignificant. But there is some promise that we might explore in future. We didn't find much when we played around with text generation. So the next thing that came to our mind, can we do something in the acoustic space? For this, Dorsa was playing around with how to stitch units from monolingual model to make code switching data. This was motivated by the unit selection framework, but we wanted to do something very simple and something different from there. What is the difference? Here we were using two monolingual data sets and multiple speakers. What we did is, given a generated or maybe real text, we tried to find those units in the monolingual corpus, cut it down, and stitch it together. To make it more intelligible, we sometimes played with different normalizing energy, adding additive noise, or others. What we saw is if we just add code switching data in the language model, the performance is not that much high, right? However, the moment we push this information in the acoustic space, we have around 10% improvement. That shows some promising result towards generating acoustic code switching data for HR. Okay, now we have seen a lot of experiment that how we can generate this data, text and acoustic space data. But can we use this in our modeling technique? We have tried to do several experiments. However, for time, saving the time, I will just mention few that Brian did during the JSALT. Here, we compared three models. First one is direct, that encoded both the monolingual models in the same space. we merged the two monolingual data and trained our CTC model. Second thing is a conditional factorized model, where what we did is we used a condition CTC for the bilingual task that is being factorized on the monolingual encoders. So over here, the performance of the model is very good, but there is one issue. The issue is if the monolingual model have any issue, let's say, error in the language segmentation, this error is then propagated to the bilingual task. And for that, we have some dependencies on the results. So what we did is, instead of any early language segmentation, we changed the model to late language segmentation. That means the monolingual model is now outputting the monolingual model is now estimating the output for its own vocabulary, whereas the bi-CTC model is actually doing the language level segmentation. So using this label, we found that the results is quite better and there is less dependency on the first stage of the monolingual model. So if you can see over here, this results is on the semi-test data set, and we have an improvement with the late segmentation compared to the language segmentation and monolingual models only. That is the direct joint monolingual model. Similarly, we can see it when we just use the monolingual data set here. So this is something we actually checked manually, and when we checked the data set, we noticed that the ASR performance is actually quite good. However, our evaluation metrics has some issues. So to do so, the next step that we did is we tried to find out what is how the evaluation metrics are correlating against the human judgment. To do so, we actually designed a guideline that follows 3 rules. One is script segregation, that is, you cannot mix two scripts if only it is not, only if it is morphological code switching, then you can do it. Else, you cannot do mixed code switching. For example, like artificial. Then the second one is rule of acceptability. So if you read the transcript, it should be enough to produce the original audio, and it should capture the intended meaning. This means there is more than one answer that is acceptable in the transcription. The third rule is rule of minimum edit. Annotators will do only the minimal edits that is required to make this utterance or the hypothesis acceptable, and this edit should be in the character level. So after we designed the guideline, we started preparing the data set. We used 3 ASR and 2 hours of speech to generate different hypotheses, and then we used this hypothesis and the minimal edits to try different orthographic, phonetic, and semantic measures. And we saw that in most of the cases, the character error rate, when used on transliteration with some normalization, plays the important part. In addition, we saw phonetic metrics were also giving much better information. We checked if this model is actually, if this guideline is actually transferable towards another language. So for that, we tried Telugu-English pairs, where we did the same steps and found that transliteration model is still scores much better. So in conclusion, we found that synthetic code switching with speech collage, that is teaching the speech units, improves the performance of the end-to-end models, we notice shared embeddings in the pre-trained MD models improves performance of the end-to-end model. So does the random lexical replacement. There is some potential, but we need to look into it further. Then we notice separate modeling of monolingual models with late language segmentation or decisions helps the code switching ASR much more than the direct modeling of both the data set. We also notice word error rate and character error rate are not adequate for evaluating CS. Transliteration and phonetic similarities shows higher correlation with human judgment, and we have noticed this in 2 language pair. However, it is not enough. We should increase our, increase our horizon and get more data that includes maybe Kosa or other language like Hindi, English. We should try more data pairs and see if these measures holds. So with this, thank you so much, and yeah.
We are a little bit short of time, but I think we have time for one very quick question. At the back. Maybe come halfway. Sorry.
Hello. Thank you so much for your talk. Very interesting. My question is related to you have some slide about the code switching and understanding. And you said that it's related to the age and gender.
Yeah.
I think there is no factors related to the historical, like more likely you have like North African, they will switch to French more than English, and
yes.
You have Indian, they will switch to English because of colonization factors.
Yes, absolutely.
The second thing for me also is related to topic. For example, North Africa will switch when it's technological thing, they will switch to English. Mm-hmm. When it's like daily life, they will switch to local language, and religious, they will switch to Arabic. This is topic really. And most of the time, code switching is related more to the low resource languages.
Yes, absolutely. That's why we are trying to go towards the zero-shot or few-shot paradigm so that we can use some monolingual data that are available with us. And about the cultural or the historical relevance, we see that, for example, when we work on Moroccan data, we see there are a lot of code switched with French. However, these data are not actual French when we say it's being borrowed and then transformed or adapted to the language. So yes, you are right, this is one of the biggest factor. However, to test this, I mean, we needed a lot of manual effort. We didn't look into it. We had data with age and gender and a few other things that our colleague looked into it. So yes.
Okay. I think we are. Thanks to the speaker again. Okay. And for more questions, don't know who gets this microphone. For more questions, I think Shamur is really busy, but you can find her probably somewhere at the conference. Okay, and show. No, it's not. Yeah, it's the last one. It's always the last one. No, this is the pair. This one. Okay. Okay, so the next presentation is by Hang Yi, who actually changed 2 presentations together for the JSALT and for the Superb Challenge. So, yeah, please take it away.
Okay. Hello, everyone. I'm Hong Yi Li. I have 2 missions here. One is talk about the Superb Challenge. It doesn't work? Hello. Yeah. And the other mission is talk about what we have done at JSALT. Because lots of things we have done at JSALT is based on Superb, so I'm going to talk about Superb first, so this will make the whole talk smoother. So let's start from Superb, Speech Processing Universal Performance Benchmark. We have a paper about the Superb Challenge in this SLT But today, I'm not going to only focus on our challenge paper. I will give the whole story about the Superb benchmark. Okay, so this is the first paper of Superb. So we have the members from many different institutes, and the senior members are Xiangwen Li from Meta, Shinji Watanabe from CNU, Abdulrahman Mohammed, also from Meta at that time, and me. And I also put the photo of the first author, my student Suwen Yang here, to highlight his contribution to this paper. Then after our interspeech paper, we have another 2 publications. One at ACL, we extend the original benchmark with more speech processing tasks, and our SLT challenge paper. So the first author is Zixuan Feng. I also put his photo here to highlight his contribution to the challenge. Okay, so let's start the introduction of the Superb. I will start from the motivation. So as you know, sales-supervised models are very popular recently. There are lots of sales-supervised models. Here, I just named a few sales-supervised models on the slides. This is not a complete list. If you want to learn more about sales-supervised models, we have an overview paper. I also put the link of the overview paper here for your reference. And usually when people propose a sales-supervised model, they evaluate their model on ASR. And they show that sales-supervised model work very well on speech recognition. However, we have a question. Are those sales-supervised models specialists only for ASR, or they are universal for all aspects of human speech? If you ask me this question before we have Superb, I will say I believe those models are specialists. I know all of you are speech experts, so you know how different it is. Speech recognition and speaker recognition are. You know how different those texts are. It's hard to imagine one model can be good at all the different speech processing tasks. But anyway, to know the answer, we evaluate the sales-supervised model. We evaluate all the sales-supervised model we can find at that time on a wide range of different speech processing tasks. So these are the tasks we evaluated in our interspeech paper. So you can find that the tasks include content-related tasks, speaker-related tasks, paralinguistic tasks, and spoken language understanding tasks. And in our ACL paper, we extend a little bit. We extend the evaluation scope to more synthetic tasks. Then before we talk about the results, let's first talk about the rules of challenge. So here the rules means how to use the sales-supervised model in the downstream task. On the web page of Superb, you can find that we have different tracks. Different tracks means different way to use the sales-supervised models in the downstream task. Actually, until now, we only open the constraint track. So in the following talk, I will only talk about the constraint track. In the constraint track, the parameter of sales-supervised model is always fixed. I know this is very different from the common approach of using the sales-supervised model. Today, you usually fine-tune the parameter in the sales-supervised model, but in the constraint track, we fix the parameter of sales-supervised model. Then if you want to do, let's say, ASR, you need a downstream model. Downstream model take the representation from sales-supervised model as input and output the transcription result. Of course, you need some label data to train the downstream model, but we do not use the label data to fine-tune the sales-supervised model. This is very different from typical approach. The network architecture of the downstream model is fixed for all different sales-supervised models for fair comparison. For example, for ASR, we always use 2-layer LSPTN for all the different sales-supervised models. And the philosophy of the network architecture choice is we want to keep the downstream model as simple as possible. People may ask, is the downstream model architecture, is the result of the sales-supervised model, is the result of the ranking of different models sensitive to downstream model architecture? The answer is Probably not. You can check our ACO paper to learn more about the analysis. Then the question is how to obtain the self-supervised representation, how to obtain the representation from a self-supervised model. Even though its parameter is fixed, there are different ways to obtain the representation. The most naive way is just take the representation from the last layer. However, in our preliminary study, we already find that this approach do not work well for some tasks. So in the constraint track, we use another way to obtain the representation. We already know that in self-supervised model, different layers learn different information. And so we need the information from all the different layers in order to solve all the different tasks. So what we did here is we weighted some all the different layers. For each layer, we have a weight. We weighted some the representation from all the different layers, and the downstream model will take the weighted sum representation as the input. And the weight of all the layers are jointly learned with the downstream model. So the downstream model selects the weight it wants to use. And we found that weighted sum is very effective in our following experiments. So before we start to look at the experimental result, people may ask why we put so much constraint, why we need a constraint track. So the idea is like this. Because we fixed the parameter of self-supervised model, we use the same set of parameters for all the different tasks we want to solve. And the capacity of the downstream model is very limited. We keep the downstream model as simple as possible. If in this case, we can still obtain good performance over all the different tasks, that means the self-supervised model can provide universal feature. They can provide a set of features that is good for a wide range of different tasks. If this is true, in the future, if you want to build a new application, you do not have to fine-tune your self-supervised model. You can just plug and play. Just train your downstream model, and the self-supervised model can serve for any new application. But this sounds too good to be true. Before we have the experiment, I think this is too good to be true, but let's take a look at the result in the constraint case. So in this table, each column represents a task. For the row, each row represents a self-supervised model. The first row is our baseline, the first row is F-bank, and the other rows are self-supervised representations. The table is sophisticated because different tasks have different evaluation metrics. So here we put the result worse than the baseline, the result worse than F-bank in black. And it is clear that there are many cases self-supervised model can outperform the baseline. And you can find that some self-supervised model achieve better performance than the baseline on all the different speech processing tasks we evaluated. So if you ask me today whether those models are specialists or universal, I would say, surprisingly, they can be universal. And so self-supervised learning is a research direction with great potential. To learn more about our interspeech paper and ACL paper, I put their video recording here for your reference. Then let's talk about our challenge. In our challenge, for each task, we have two data sets. One is public data set. For public data set, we use open data. In our interspeech paper and ACL paper, we report the results on the open data set. So for the participants, if you want to use the open data set, you train because the data is open, so you can easily access the data. So you train the downstream model yourself. During training the downstream model, you need to select hyperparameter like learning rate. So you also handle this part yourself. And you get the result on the testing set, and you only submit the result to us. However, if we only have the open data set, we doesn't know whether those self-supervised models are overfit on the open data set. because the participants can decide how they are going to train the downstream model. We only define the network architecture, but you can search the hyperparameter yourself. We don't know how hard the participants search the hyperparameters. And if you search the hyperparameter very hard, probably the result is just overfitted on the open data set. So we have a hidden set. For the hidden set, this is collected with LXT. So we have a hidden set which is not public available. To evaluate the result on the hidden set, the participants give the super team your self-supervised model. You submit your self-supervised model, then we will train the downstream model for you. So this can make sure for all the self-supervised model, the downstream model training policy is the same. So different self-supervised model can be compared in a fair way. And this is the link for model submission. Thanks for Hugging Face to cooperate to working on this submission system. And because to train the downstream model also need actually lots of computing resources, so the team want to thank Taiwan Web Service for support of the computing resources. And this is the super leaderboard. So on the leaderboard, we have a table, and in the table, we try to rank the model. We have a score, because there are many different speech processing tasks. So we try to have an overall score to rank the self-supervised model. We do not have time to go through this overall score. The basic idea is different speech processing tasks has different evaluation metrics. We try to normalize them into the same range and average the normalized score. And we call this score super score in the following talk. Besides the table, you can also generate radar chart on our leaderboard. So this can make you easier compare different models. You can know what is the strength and weakness of each model. And we also have this scatter chart. For this scatter chart, each point represents a self-supervised model, and the vertical axis is their performance. You can choose you want to show the performance on a specific task or you want to show an overall score. The horizontal axis is the computational cost or the model parameter of a self-supervised model. So here, we want to show that we not only care about the performance of those self-supervised model, we also care about how large it is or how many computational costs it is required. And due to time limitation, for the result of the challenge, I do not really have time to go through the detail. I will go through it in a very short, brief way. So for the public set, now the best model is WebLN. It is the best one on almost all the tasks. And it is the best one on almost all the tasks on public and the hidden set. There's only a few exceptions. On the public set, data to vec is the best on ASR. And on the speech enhancement task, CCC Web to Vec 2.0, they also have a paper in this SLT. They are the best on the speech enhancement. And this is the overview of the performance of all different models on the hidden data set. Until now, we have more than 30 models submitted to this hidden set leaderboard. If you want to know the detail of all the models, we already put them in our SLT paper. Here, I can show you that you can tell that we have a very wide range of submission from a very small model to a very large model. And the best one, the one with the best super score is WebLN large. And to learn the detail of those models, you can check our paper. I will also talk about some of the models in the following report for the JSALT team. Then I have some future work. Probably I can very briefly go through it. So this is something we are thinking about. So the current super challenge only include English data. So one potential future work, actually it is already ongoing, is extended to multilingual. And there are other future work we haven't started yet. One is consider super with resource constraint. As you know, now people train large self-supervised model. Academics don't have a chance to compete with the industry. So how about we have a competition? Let's say you can only use a specific amount of data, use a specific amount of computation. Let's invent the most efficient algorithm to train a self-supervised model. Okay, there are other possible future work, but due to time limitation, probably I can skip this part. So if you want to start to working on self-supervised speech representation learning, let me introduce you a very useful toolkit called S3PRL, which is developed by NTU student Shuwen Yang and Andy Liu. In this toolkit, you can access to a wide range of different speech self-supervised model and apply them to a wide range of different speech processing tests. If you want to start to working on super challenge or other application, this toolkit will be very helpful. So this part is for Superb. So do we want to take some questions here, or we can switch to the JSALT report, then we can take the question in the end?
I think this is up to you. Do you want to continue?
Let's switch to the JSALT report first, then I
think
take
so
the
too,
question.
yeah. We are a little bit behind. Oh, yeah, sure.
Okay, now we already introduced Superb. Then I'm going to talk about what the pre-training team at JSALT have done this summer. And to learn more about this amazing team, I also put the webpage of the team in the slides. So please check our webpage to learn who are the members in the team. So this is our goal. Our first goal is we want to investigate an effective way to use self-supervised speech model. And we want to reduce the computation requirement of those speech self-supervised model. And the third goal is we want to evaluate and even improve the generalization capability of self-supervised model. And we want to leverage multimodality information, for example, text and visual information, to improve the pre-training of those self-supervised model. And we want to extend the application of self-supervised model to more applications we haven't touched yet in the Superb Challenge. And I'm very proud of the team. We submit 5 papers to SLT during last summer, and all of them are accepted. And also very honored to mention that one of the papers won the Best Paper Award at SLT. Thank you, thank you, thank you, thank you. And I have to say, I give the credit to this amazing team. And in all the beginning of the direction, I will I will share the photo of who is working on this direction. So our first direction is we want to investigate how to effectively use self-supervised model. This direction was led by Xiangwen Li, Daniel Li from Meta. And as you know, there are many ways to use self-supervised model. In this figure, I show 4 different ways. Yellow blocks means the parameters are fine-tuned with the downstream model. Gray bar means the parameters are fixed. And the most common way is the left one, which is fine-tune the whole model. And we also introduced how we use self-supervised model in the Superb constraint case. But there are other efficient approach. One is adapter. So adapter means you insert a small module into your self-supervised model, and you only train the small module during the downstream task. And another approach is called prompting. Prompting means you always fix your self-supervised model. You don't touch your self-supervised model. You only modify the input. You add an extra input called prompt, and you use the prompt to modify the output of self-supervised model. And adapter and prompting has been shown to be very useful for text pre-trained model. But they are not widely investigated on speech. So we want to know whether adapter and prompting are also helpful for speech self-supervised model. And this is our result for adapter. If you want to learn more about this paper, if you want to learn more experimental result, please check our paper in SLT. Here, I just briefly summarize the result in one page. We try to investigate all types of different adapters. And here I show the result of speaker identification. So here we use the superb public set. And the vertical axis in the figure is the accuracy. So the larger, the better. And you can find that the red point is the result of fine-tune the whole model. And the result in the blue box are the result for different types of adapter. And you can find that most of adapter can outperform fine-tuning on speaker identification. We also investigate other tasks. You can check our paper for more detail. So this shows that there are other ways other than fine-tuning. If you are still using fine-tuning, you can try other approach to get better performance via self-supervised models. Another way we investigate is prompting. So this animation shows the idea of prompting. So the performance, we try to prompt spoken language model, and the parameter of spoken language model is always fixed. We only modify the input, and you modify the input, you can make the spoken language model to do different speech processing tasks. Last summer, we only tried 2 tasks, but then we extend the same idea to 17 different tasks and submit a paper to ICASP. Then the second is we want to reduce the computational cost of self-supervised model. Because from this figure I just showed you, it is very clear that larger model, the model with more computational cost, achieve better performance. However, can we put a spot here? Can we have a self-supervised model which is small, which is efficient, but also have good performance? During the summer workshop, we tried to explore many different ways to compress the model. We tried weight pruning, head pruning, low-rank approximation, knowledge distillation. We also tried to modify the network architecture of self-supervised model. As you know, today, in most self-supervised model, you have a convolutional layer to deal with the input waveform. Then we remove convolutional layer, replace with the male spectrogram as the input, try to reduce the number of parameters. And we summarize all our effort and submit a paper to ICASP. And we also invent a new idea to reduce the computation of self-supervised model. So you can check our SLT paper for more information. The basic concept is like this. As you know, for self-supervised model, because we are processing speech, it's a sequence of vector, so usually we use transformer layer. And for the transformer layer, the input and output are both vector sequence, and they have the same length. And as you know, the computational cost of transformer is highly dependent on the input sequence length. Can we reduce the length of the sequence? We propose a learnable subsampling module. So we can apply this subsampling module, which is learnable, which is learned from the data. This module will delete some of the representation. It will make the representation sequence shorter, but still keep the useful information. Because we have a shorter representation sequence, the following layer, the following transformer layer, only need to do less computation. We use this way to reduce the computation of self-supervised model. And we try to put different approach together to see how small a model can be. So actually, the smallest model on the super leaderboard is submitted by the JSALT team. And it has better performance than the second smallest model, which is modified CPC. And I want to highlight that actually modified CPC uses much more data than we do. And the third direction is about the generalization capability of self-supervised model. And here for generalization capability, I mean, when you use a self-supervised model in downstream tasks, you have a label data set and a testing set. What would happen if the label data and testing set are mismatched? Can self-supervised model handle this kind of situation? There are many different types of domain mismatch. Due to time limitation in the summer workshop, we only focus on speech distortion. So our setting is, in each downstream task, our label data are clean, but our testing data have all different types of speech distortion. In this case, can self-supervised models still achieve good performance? Then let's take a look at the result. Here we report the result of ASR on superb public set. For the blue bar, we have the result of the Huber, public available Huber. And you can find that although it worked well on clean speech, if you apply all different types of speech distortion on the testing set, I want to highlight again that we train on the clean set, we train on the clean label data, but evaluate on the distorted testing data. So if the testing data have distortion, of course, the performance of ASR degrade in all different cases. However, we find a very simple way to make the self-supervised model have better generalization capability. The idea is like this. Given an off-the-shelf self-supervised model, do not directly use it. You continue pre-train the self-supervised model with some noisy data. And we find that this approach is very helpful. So for all the different distortion on the testing set, this approach can reduce the word error rate remarkably. And we also evaluate not only on ASR, but other super tasks, and we have the same conclusion. Another thing we did during the summer workshop is we try to improve the generalization capability of compressed model. We propose an approach called cross-distortion mapping. This is also published in this SLT. Due to time limitation, I think I have to skip this part. We submit the result of cross-distortion mapping to the superb leaderboard. So the result is the model is number 15. You can find that if we consider the small model, if you consider the model smaller than Huber, actually the model with cross-distortion mapping achieves the best performance among all the models smaller than Huber base. Then the fourth direction is leverage multimodality data. Let's start from leverage text data. This direction has many senior members, include Andy from Meta, Paul Agasha from JHU, David Howard from UT, Shinji Watanabe from CNU. And as you know, there are already lots of speech text joint pre-training model. Here, I just list a few. And in the summer workshop, we have another idea. We consider unsupervised ASR as a self-supervised model. So this is our idea. As you know, the pre-trained speech model is trained by unlabeled speech data. And now let's say you have some text data, but I have to emphasize that the text data is unpaired with the speech. The text data is not a transcription of the speech. The text data and speech data, they are unrelated, they are unpaired. With unpaired text data, one thing you can do today is you can apply unsupervised ASR, like Web2Vec-U. I know it is very popular today, so I probably do not have to describe what is Web2Vec-U. So you can apply unsupervised ASR technique. You can have a generator take the representation of self-supervised model as input and output the transcription. And during the summer workshop, we implement an ESP.NET unsupervised ASR open source toolkit. So hopefully we can make the community implement unsupervised ASR easier in the future. And we also submit the paper to ICASP. And because the pre-trained model and the generator for unsupervised ASR are both trained without labeled data, the generator is trained with the text data, but it is not the transcription of speech. It's trained with the unpaired speech and text data. So we can consider the pre-trained model and the generator all together as a self-supervised model. And we can think even more. Now the generator can output text transcription. How about we apply a pre-trained text model like BERT or T5 on top of the generator? And those models are trained only by text data, so they are also self-supervised. So you can consider pre-trained speech model, generator, pre-trained text model all together as a very large sales-supervised model. And this sales-supervised model takes speech as input, and it processes the speech all the way to semantic representation. And we find that this kind of model can be very helpful for spoken language understanding. To learn more about how this model can improve spoken language understanding, please refer to our ICAS submitted paper. We already put the paper on archive. Then let's talk about leverage multimodality data, but use the visual information. I know use the visual information to improve the training of sales-supervised speech model is not a new idea. There are already lots of publications use visual-grounded speech data to improve the training of sales-supervised speech model. In the summer workshop, what we want to think about is people use visual-grounded speech data because it is cheaper to collect it than text transcription. There's another type of data which is also easy to collect, which is visual-grounded text data. So we try to leverage visual-grounded text data to improve the performance. And to learn more about how can visual-grounded text data can improve the performance, please check our SLT paper. And we also extend the idea to multilingual, and we submit the paper to ICAS. You can check the result in our archive paper. Okay, so last but not least, we extend the application of sales-supervised model to use the sales-supervised model on prosody. And due to time limitation, I truly do not have the time to go through it. However, you can check our SLT paper. I just used 2 sentences to summarize our finding. The first sentence, whether sales-supervised model contain prosody feature? Yes. And even though your model is trained on English, they extract prosody feature for other language like Chinese. And with sales-supervised model, we can achieve SOTA on several audio-only prosody-intensive tasks. I need to skip the summarization, and this is the acknowledge for the JSALT workshop, and we want to thank for NARCC for providing computing resources. We also want to thank for Taiwan Web Service to support the computing resources during the summer workshop. And I want to stop at this webpage, this slide, so if you are interested in sales-supervised representation learning, don't miss those events. Thank you.
Thank you, Hangi. I think we have time for one question. Do we have a question? Oh, over there.
I'm just curious on the evaluation. Since the data set is not fixed, and so the best is Microsoft is a 600 million parameter, I'm sure trained on data that others were not trained. So the leaderboard doesn't tell you much about which technique is better than the other. It only tells you that more data and more parameters is better than the other. So you can comment on that.
I totally agree with you, and you are probably the 100 people tell me this, so I totally agree with your opinion, because now people can use whatever data set you want, use whatever large your model you want to train a sales-supervised model. So the comparison is not fair. I totally agree with it. So this is why on our leaderboard, we not only show the performance, we have a scatter plot to show the computational cost. So you can easily tell the trade-off between the computational cost and the performance. In the future, we will probably add another dimension about the amount of data you use. And so this is why in the future work, we are considering have a resource constraint superb. That means for all the different teams, let's just use the same amount of data. Say, we can only use library speech 916. No, don't use other external data. And for the computational cost, we limit the computational cost. For example, you can only train on this machine for 3 days, something like that. Then we can have a more fair comparison about the algorithm. Hopefully we can have this kind of competition, this kind of challenge in the future. I hope I answered your question.
Okay, thank you, Hongyi. So this concludes the session on the JSALT and the Superb. They are all around, so if you have more questions, you can ask them during the coffee break or during the poster session. Let's thank the speaker again, and everybody. Enjoy the last day of SLT.
هترجع الصوت ولا ايه؟ الصوت هترجعه هنا ولا ايه؟ لا مش محتاج.
All right. So now we are having the coffee break. I'd just like to remind everybody that we have the survey here. So it should take from you a minute. So whenever you have a chance, please fill the survey for us. Thank you.